In this video, we're going to learn dimensional analysis, which is the strategy for performing unit conversions. To begin, we need to recognize that units behave very much like variables that you may have seen in algebra. For example, if we have like variables, we can combine them. 2x plus 3x equals 5x. Similarly, if we have measurements with the same units, we can add them. 2 milliliters plus 3 milliliters equals 5 milliliters. However, if we have unlike variables, such as 2x plus 3y, we cannot combine them. The same is true for units. 2 milliliters plus 3 grams cannot be added because the units are different. When multiplying, unlike variables can be combined. For example, 2x times 3y equals 6xy. Likewise, different units can be multiplied. 2 kilograms times 3 liters equals 6 kilograms times liters. If the same unit appears twice during multiplication, the unit becomes squared. Division works similarly. When dividing, we simply simplify the coefficients and the units. 6x divided by 2y equals 3x divided by y, and 6 grams divided by 2 milliliters is equal to 3 grams per milliliter. If the same unit appears in both the numerator and the denominator, it cancels. 6x divided by 2x is equal to 3, and 6 grams divided by 2 grams is equal to 3. Now let's look at a practice problem that focuses on the units. Based only on the units, what is the answer to the following calculation? 5 milligrams times 2 liters divided by 1 gram. The answer choices include liters, milliliters, no unit, or milligrams times unit, times liters, or impossible. To solve this, we need to identify the prefixes versus the units. The prefix milli means 10 to the third. That means that 5 milligrams can be rewritten as 5 times 10 to the minus 3 grams. Rewriting the entire expression gives 5.0 times 10 to the minus third grams times 2.0 liters divided by 1.0 grams. The grams cancel, leaving liters. Numerically, this becomes 10 times 10 to the minus third liters. Since 10 to the third corresponds to the milli prefix, this is equal to 10 milliliters. In many situations, the same physical quantity can be expressed using different units. For example, distance can be measured in feet, inches, meters, or centimeters. The relationship between two units is written as a conversion factor, which is essentially a proportion. For instance, 1 foot is equal to 12 inches. This relationship is always true. 2 feet is 24 inches. 3 feet is 36 inches. And so on. It's always a 1 to 12 proportion. Conversion factors help us convert from one unit to another, no matter how much we are starting with. Dimensional analysis is a problem-solving strategy where we analyze units to determine which conversion factors to use and how to arrange the conversion factors mathematically. You are expected to use dimensional analysis throughout the semester. Let's look at an example. A patient weighs 99.2 kilograms. How many pounds does the patient weigh? We need conversion factors. 1 pound is equal to 453.59 grams. And 1 kilogram is equal to 10 to the third grams. Using these relationships, we can first convert from kilograms to grams, and then from grams to pounds. Rather than doing multiple mathematical calculations, we can organize our numbers in a table with 2 rows. The rows represent numerators and denominators of fractions. We start with the given value of 99.2 kilograms from the question prompt and arrange our conversion factors so that the units cancel diagonally. Having the same unit in the numerator and the denominator allows these two units to cancel out and become 1. Kilograms cancels with kilograms, grams cancels with grams, and we are left with pounds. Match the numbers from the conversion factors we had earlier. Each conversion factor should be in its own column. When it comes time to enter this into your calculator, remember that the table is really just fractions in disguise. The top row of the table is the numerators, and the bottom row is the denominators. If your calculator can do two-line fractions, I recommend typing in the math as it appears on your paper. If your calculator only displays single lines of math, multiply the numbers across the top and then divide by all the numbers on the bottom. After performing the calculations, we obtained 215.84 grams. Since the original measurement had 3 significant figures, we round up to 216 pounds. Sometimes units of a number contain a per or division symbol. These compound units represent relationships between two units and act as conversion factors. Density is a common example. The unit grams per milliliter can be written as grams divided by milliliters on one line or two lines, or grams times milliliters to the -1 exponent. All of these mean the same thing. 7.8 grams of this material has a volume of 1 milliliter. This is a relationship or conversion factor between two different units. Here's another example. The density of a metal object is 7.8 grams per milliliter. If the object has a mass of 12.12 grams, what is its volume in milliliters? Our first step is to identify the given unit and desired unit. The question asks us to find volume in milliliters, so that is our desired unit. But what is our given unit? We are given two different numbers in this question, so let's analyze the units. Notice how the units of one of the values has a division symbol in it. This tells us that that value is a conversion factor because it is relating two units to one another. Our given value must be the simple unit grams. This tells us immediately that grams must cancel and milliliters must remain, and density is going to be our tool to do that. Start your setup by filling in the units. Your given value is in the numerator at the start of your calculation, with conversion factors to the right. The last unit in the numerator should be our desired unit of milliliters. We want grams to cancel, so grams must appear in the denominator. We intentionally invert or flip density, 1 milliliter divided by 7.8 grams. This is not random. This is done so that grams cancels. With the numbers in place, our setup is 12.12 grams times 1 milliliter divided by 7.8 grams. The grams cancel, milliliters remain. This confirms that the setup is correct before doing any math. Lastly, calculate and round. The calculator says 1.5538 milliliters. Density has two significant figures, so we report our answer as 1.6 milliliters. Dimensional analysis becomes especially powerful when multiple conversion factors are required. Let's work through a longer example. A toilet is flushed 29 times in 6 days. On average, each flush uses 4 sheets of toilet paper. A package of toilet paper from Costco contains 30 rolls. One roll has 425 sheets. At the beginning of the COVID-19 pandemic, someone stockpiled toilet paper. How many years will 13 packages of toilet paper from Costco last? We begin by identifying relationships by reading through the question sentence by sentence. 29 flushes is equal to 6 days. 1 flush is equal to 4 sheets. 1 package is equal to 30 rolls. 1 roll is equal to 425 sheets. We can create a solution map starting from packages and ending in years. To come up with this map, we are matching units we see in our conversion factors. We have a conversion factor that relates packages to rolls, and another conversion factor that relates rolls to sheets, and sheets to flushes, and flushes to days. We also need a time conversion to go from days to years. 365 days is equal to 1 year. Our final solution map is packages to rolls to sheets to flushes to days to years. Our conversion factor table needs to start with our given value from the question prompt, 13 packages, and end with the unit of years. We will use conversion factors in the same order that is shown on our map. Each arrow in our map corresponds to a conversion factor. We can always look at the numerator of the previous conversion factor to help us decide what goes in the denominator. We want the same unit in the numerator and denominator so that they cancel out. Our map reminds us about what unit goes in the numerator. Our first conversion factor will put rolls in the numerator. Then sheets will be in the numerator. Then flushes, days, and lastly years. Match the conversion factors to the table. Each conversion factor will be in its own column. Pay attention to the units when placing numbers to make sure that the number goes next to its correct unit. We will end up with 13 packages times 30 rolls divided by 1 package times 425 sheets divided by 1 roll times 1 flush divided by 4 sheets times 6 days divided by 29 flushes times 1 year divided by 365 days. After performing the calculation, we obtain 23.488 years. Because many of these quantities are exact counts, let's not worry about significant figures for this problem too much. Let's just say that's close to 23 years. Dimensional analysis works even when the units are unfamiliar. Let's solve a problem using fictional units so we can focus on the logic and process. There are 4 darsecs and 3 francs. It takes 4.5 francs to make 2 ren. 3 leks are equal to 7 ren. How many darsecs are in 32 leks? We identify the conversion factors. 4 darsecs is equal to 3 francs. 2 ren is equal to 4.5 francs. 3 leks is equal to 7 ren. Our given value is 32 leks. And our final unit needs to be darsecs. Any other units are just intermediate units needed to establish a link between our given and desired units. We create a solution map by looking at our conversion factors and seeing what we can relate each unit to. Sometimes you work backwards, sometimes you work forwards. In this example, I'm going to work backwards since my brain is focusing on how I can get to darsecs. I can get into darsecs from francs. I can get into francs from Ren. And lastly, Ren relates to Lex. My final solution map is Lex to Ren to Frings to Darsex. This solution map has 3 arrows indicating 3 conversion factors. The solution map indicates what units will be in the numerator so that we can fill out our table. Remember that for a unit to cancel, it must appear in the numerator and denominator. We aim for the units to cancel in a diagonal fashion so that each conversion factor stays in its own column. Again, I'm going to work backwards. I know that the final unit I want is Darsex, so I know it must be the last unit in the numerator. I have a conversion factor that relates Darsex to Frings. If Frings is in the denominator here, it must be in the numerator of the adjacent conversion factor. I have another conversion factor that relates Frings to Ren. If you get lost, remember that we did come up with a map from earlier. The units in the map should match the numerators of our table. Match the numbers to the conversion factors that we had earlier, making sure you use each number only once, and maintain true relationships in each vertical column. We end up with 32 Lex times 7 Ren divided by 3 Lex times 4.5 Frings divided by 2 Ren times 4 Darsex divided by 3 Frings. Remember that the table just helps organize our numerators and denominators. Multiply by the numerators and divide by the denominators. Double check that your units cancel before entering this into your calculator. You should get 224 Darsex. Notice that we did not need to know what the units represent, only how they relate to one another. Often we work with SI unit prefixes. When converting between prefixes, it is often easiest to stop at the base unit first. For example, an infant's head circumference is 40.6 centimeters. How many millimeters is that? First, recognize that cm and mm are different prefixes of the same unit, meters. The prefix centi means 10 to the minus 2, and milli means 10 to the minus 3. 1 cm is equal to 10 to the minus 2 meters, and 1 mm is 10 to the minus 3 meters. Conceptually, 1 centimeter is larger than 1 millimeter. We are going from a bigger unit to a smaller unit. Expect the numerical value to become larger. We can set this up using dimensional analysis. By using dimensional analysis, we let the units guide our setup, so we do not have to memorize equations or try to remember if we multiply or divide. We will follow the map cm to m to mm. We convert centimeters to meters, and then meters to millimeters. We put our units from our solution map in the numerator and the units we want to cancel in the denominator. Like in past examples, each conversion factor will be in its own column. After we get our units in the correct locations, we match the numbers from our conversion factors. Although you may be tempted to reach for a calculator, it isn't necessary for this problem because the conversion factors are exponents of the same base, 10. Based on the quotient rule of exponents, we can subtract the exponents. 10 to the minus 2 divided by 10 to the minus 3 is equal to 10 to the 1 because negative 2 minus negative 3 is the same thing as negative 2 plus 3, which is 40.6 times 10 to the first. which is equal to 406 millimeters. The original value has 3 significant figures, and so the final answer is reported as 406 millimeters. The numbers in the conversion factors are exact numbers with unlimited significant figures. Now let's convert 2.75 kilometers to inches. The required pathway is kilometers to meters to centimeters to inches. This pathway tells us that we need 3 conversion factors. So let's write those out. 1 kilometer is equal to 10 to the third meters. 1 centimeter is equal to 10 to the minus 2 meters. And 1 inch is 2.54 centimeters. As with before, the solution map tells you what unit should be in the numerator next. The previous unit should go in the denominator. Then we match the numbers from our conversion factors. 2.75 kilometers times 10 to the third meters divided by 1 kilometer times 1 centimeter divided by 10 to the minus 2 meters times 1 inch divided by 2.54 centimeters. Calculating gives 108,267,000.7165 inches. Rounding to 3 significant figures gives 108,000 inches, or 1.08 times 10 to the 5th inches. When converting area or volume using distance conversion factors, remember that conversion factors must also be squared or cubed. A square that is 1 centimeter by 1 centimeter has an area of 1 centimeter squared. However, 1 centimeter is the same thing as 10 millimeters, so the same square could be measured in millimeters, and we would have 10 by 10. 10 times 10 is 100. That means that there are 100 millimeters squared, not 10 millimeters squared. If you are using distance conversion factors for area, you need to square the unit and the number. Think of the unit and number as being in parentheses. Exponents outside the parentheses get distributed in based on the power rule of exponents. If you are using distance conversion factors for volume, you would need to cube the unit and the number. If you see a number written like 100 millimeters squared, the squared only applies to the unit. Finally, temperature conversions require equations rather than dimensional analysis alone. The constants in these equations are exact. However, you can figure out what equations to use by analyzing the units in each equation. On a hot summer day in Fresno, the temperature is 113.0 degrees Fahrenheit. What is the temperature in Kelvin? With the equations provided, we have a way to get to Kelvin from Celsius. So first we need to convert Fahrenheit to Celsius. Degrees Celsius is equal to Fahrenheit minus 32 divided by 1.8. Plugging in our temperature, 113 minus 32 divided by 1.8 is equal to 45. Based on the addition and subtraction rule, our numerator is significant to the tens place because 32 is exact. This difference is 81.0, which has 3 significant figures going into the division rule. Our answer is 45.0 degrees Celsius, which has 3 significant figures. Next, convert Celsius to Kelvin. Kelvin is equal to Celsius plus 273.15. 45.0 plus 273.15 is equal to 318.15 Kelvin. Based on the addition rule, our answer is significant to the tenths place because our measured value is 45.0. The 273.15 is exact. Rounding to the tenths place, the final answer is 318.2 Kelvin.